And you can see. No, I don't use it right now. Huh? I know. What are the chairs on the chair company. यहाँ पे थोड़ा सा इधर कर लो, इधर आ जाओ, वहाँ तो खड़े आ जाओ यहाँ पे 2 सीट खाली है। ऑनलाइन भी ले सकते हैं। और कौन सा वाला है? हॉल वाला लेके आ पाओगे? ऑडिटोरियम में देखो कितना आ रहा है, देखो 2-4 मिनट आ जाएगा यहाँ पे मैं इधर बैठ सकता हूँ। और कुछ प्लास्टिक का में लगा देख लेते हैं। और देखो कुछ आए तो ये वाला आज पे कितना भरा नहीं देखा मैंने। जितना यहाँ पे आ जा रहे हैं ऑडियंस कम होते थे, आज देर कम हो गए। They told this is there's a seminar workshop going on.
Yes,
teacher
yes,
study
yes.
program. Panel discussion is there now, so there are more number of participants, 40, 50 something. वो बेटर है, वो ठीक है। यहाँ पे तो 2-3 आ जाएंगे। हाँ नहीं आ जाएंगे। प्लास्टिक तो बहुत ही नीचे है। उधर एक आ जाएगा, उसमें 1-2 हमका नीचे प्लास्टिक से बहुत ही आ गई सब। सवा नहीं। यार बैठ जाओ, दो जो आ जाओ, बाकी ठीक बालकनी आ जाए ना। मूवी में बालकनी में देखते रहे। यहाँ लगा है तो अच्छी, वहाँ पे भी लगा सकते हैं। इधर लगा ना, ये थोड़ा भारी है तो साइड में यार आ जाओ। So we unmute this one. एक और है यहाँ, अच्छा ऑनलाइन भी है तो, और एक पार्टिसिपेंट ऑनलाइन अटेंड कर लेते हैं। अनम्यूट बैठ जाते हैं यहाँ पे। Your computer, right? Yes. The speakers will be on. This computer. Yeah, you should unmute. So that's fine. Here you unmuted, right? Audio is on.
This is muted.
Muted, and
Yes.
this one is muted.
Yes. Audio is completely off.
Okay. So very good afternoon, everyone. Welcome to today's seminar. And today we have Dr. Kishalay from USA. So Kishalay obtained his undergraduate degree in physics from IIC Bengaluru, and then he moved to USA, Caltech. So he obtained his PhD in 2021 in astrophysics from Caltech. And then he joined as a NASA Einstein Fellow, as well as he was MIT Kavli Institute postdoctoral fellow at MIT, USA. Into 2025 beginning, he is going to join as a faculty at Columbia University and with the Center for Computational Astrophysics in New York City. Right? So congratulations for that new position. So as per research interest, he specializes in wide field imaging survey to uncover stellar explosion across our galaxy and beyond. So his research work includes observational time domain astronomy, and he's leading large programs. For example, largest ground-based survey programs like Cake, Gemini, Magellan, as well as space-based surveys like NEOWISE and JWST telescope he's using. So he's mostly studying transiting sources, starting from nova, supernovae, and TT, tidal eruption event. So we'll hear more from him, and so you can start your presentation.
Thank you. It's a pleasure to be here because, as I've been telling everyone I've met so far, that my career in astronomy actually started here because I was a summer intern here in 2013. When I spent 3 months at ADS using the 40-inch telescope, which is up there. That was the first telescope I ever used, and then of course that was the starting point to bigger and bigger telescopes. And it's a pleasure to be back here and talk about how things have evolved over the years, and specifically talking about this field of time domain astronomy and why it's so exciting today, and why making discoveries every day. That's how rich the field is when you look at the field observationally. So I'm going to try to start by convincing you that that time domain astronomy is not only interesting, but by pushing time domain astronomy into new regimes, we are essentially fundamentally completely changing our view of how stars live and die in the universe. And hopefully all of you have seen this plot in some form or the other.
ये वाली UBS है वो उधर.
There you go. Thank you. Yes, so hopefully all of you have seen this plot in one form or the other. This is the stellar life cycle, very layman's overview of what the stellar life cycle looks like. For low mass stars like the sun, they eventually evolve to become red giants. They expel out their outer envelopes, left behind with a white dwarf. Things that are more massive, probably more than about 10 times the mass of the sun. They do more exotic things. They undergo supernova explosions, probably, and then turn into neutron stars and black holes. But what I have been interested in the past few years is in time domain, and in particular, using infrared time domain surveys, where not only are we looking at the sky again and again, but we use infrared instruments to do that. And what I'm going to try to convince you over the next 40 minutes or so is to convince you that infrared surveys are completely changing our view of what this stellar life cycle looks like, and why the infrared surveys, and why there's so much of new instrumentation that's being put into infrared searches, because there's so many unanswered questions about this picture that can be addressed. And in case you are under the wrong impression that all of this is a very smooth and serene process and everything happens very calmly, I'm going to try to convince you that every step of this process involves an explosion in one form or the other. So there are things going boom in the night sky that are essentially marking each and every step of the process, and how infrared surveys are completely changing our view of what this life cycle looks like. So I want to start by telling you a bit about the discovery engine that's going to be the focus of this talk. And a lot of this actually has been done using completely public data. What that means is that these data sets have been essentially lying around in the archives for anyone to explore. You can just go on the internet, download these data sets. And just to give you a sense of how big the field has become today, that you could be anywhere in the world and doing time domain astronomy using publicly available data sets. The one that is my favorite right now is this survey called NEOWISE. So for those of you who haven't heard, NEOWISE is a mission that was launched in 2009, almost 15 years ago by NASA. It was meant to survey the sky in the mid-infrared, and then it was rejuvenated in 2014 to look for asteroids. So NEOWISE was not really meant to be a transient survey. It was meant to be an asteroid discovery machine. But what has happened is that over the course of its survey, essentially you've been able to, what the telescope does is that takes one image, mid-infrared image of the sky in two wavebands. This is 3.4 and 4.6 microns. These two are completely in the mid-infrared, very difficult to observe from the ground. But because it's in space, what it does is that it has this orbit that goes around the Earth. And because it has this polar orbit, imagine as the Earth goes around the sun, you get one image of the sky every 6 months. So every 6 months, you get one image of the sky in 2 filters. And that's it. That's all it is. And what we have done essentially is to take these images that NEOWISE has acquired over the last 15 years and do image subtraction on them, trying to discover transients in the NEOWISE data directly. The way that looks like, for those of you who haven't done image subtraction, it looks roughly like this. You start off with an image of a part of the sky that looks like this. You compare it with an image taken 10 years ago, and you subtract the two, you see that every now and then there'll be sources that stick out. These are essentially things that are sticking out in the subtraction, telling you that something has changed in this part of the sky. And just to show you how powerful this technique is, you can essentially take two identical looking images. This is a nearby galaxy, 40 megaparsecs away. By eye, there's absolutely no difference between them. But as soon as you subtract the two images, you see that there is something sticks out in the middle of the image. We won't get to talk about this, but this happens to be the nearest tidal disruption event that has ever been discovered, just lying around in the WISE data because nobody was looking at it. So so when I started this project about 2 years ago, maybe 2.5 years ago, what we started trying to work with. Give me more chance. Now you have to give
this. Yeah. That is a different meeting. So there's steering committee meetings. So I think they are
right. So when we started this project, what we soon realized when we started processing these data sets is that there are of the order of a few million transients in the WISE data set that had essentially been unnoticed for years until we started doing this systematic exploration of what these mid-infrared transients are.
So Kishalay, how did you make this reference image for?
So that most of that work was done by Unwise.
Okay.
So the Unwise team have been creating these deep stacks of WISE data. So these are actually just Unwise images. What I did was I just took two Unwise images and subtracted them. And that's what you get once you do that. So I've made friends with the Unwise team, and they've been very kind to help us with this project. Right. So the only reason why we've been able to make any sense of these transients is because we've had a panchromatic follow-up program from the ground and in space. And it really goes all the way from small telescopes, 2 to 3 meter class telescopes, all the way to the biggest 8 to 10 meter class telescopes on the ground. And going across the wavelength range, going from radio to submillimeter to X-rays to understand what these events are. Because the thing to keep in mind is that when you're discovering sources in a wavelength range that is not visible from the ground, it becomes very difficult to understand what they are because you're finding them in a wavelength range that you can't observe from the ground. So you really have to go as far out as possible to make any sense of what these transients are. So again, this is all possible because of this amazing team of scientists, students who've worked on the various aspects of this project. They probably have done more work on this than I have. I just sort of try to figure out what is interesting, and they do most of the work. But I'll try to sort of highlight many of the contributions that these folks have made to this project. All right. So this is going to be the central line of the story for today, which is I'm going to try to convince you about how infrared surveys are changing each and every step of this stellar life cycle process. And I'll start with perhaps something that is probably the most obvious to you, which is where do we expect to see explosions in this life cycle? And that is somewhere over here, which is when massive stars die, they undergo supernova explosions. Well, they probably undergo supernova explosions and turn into more compact remnants like neutron stars or black holes. But on this same note, I want to start with a very, very fundamental question, which you might think it has a simple answer, but there is no answer to it yet, which is we sort of paint this picture of, yes, massive star, supernova turns into a neutron star or black hole. But if I asked you this question, which stars form neutron stars and which stars form black holes? What do we know about this observational? Turns out the answer is highly non-trivial because we know almost nothing about this. What produces, which stars produce black holes and which produce neutron stars. There have been sort of broad theoretical ideas about what this might look like. And the landscape looks. This is a plot from a review article that appeared more than 20 years ago. What you're seeing here is
Continue.
Okay, yes. Okay. What you're seeing here is a plot from a review article more than 20 years ago, which is if you asked, what do we think, what stars turn into neutron stars and what turn into black holes? This is what that landscape looks like, which is you plot the metallicity of the star against its mass. We think that the most massive stars above maybe 25 solar masses or so, they collapse into black holes, not really undergo supernovae. Whereas the lower mass stars, somewhere between 10 and 20 solar masses, most of those turn into neutron stars. But again, this is completely a theoretical picture. There is almost no observational evidence that says that this star produced a supernova that eventually left behind a neutron star or a black hole. And even though this picture looks very elegant and you would like to believe this picture, it turns out that if you look at real numerical simulations of massive star explosions, the picture is much more complicated than this. This is a plot from a paper from last year, which shows what we think produce neutron stars and black holes. What you see here is that unlike these islands of, beautiful islands of where stars explode and don't explode, what the situation in theory probably looks like is more of these picket fences, which is if you scan across the mass of the star, in some ranges, the stars explode, in some ranges, they collapse, leaving behind black holes. And there's no really clear description. In fact, there are suggestions that this process might even be chaotic in some ways. The same star could turn into a black hole one day and the neutron star then on another day. That's how little we know about this process. So the reason, of course, what I find this interesting is that we know black holes exist, and clearly there's some, we know of supernovae that have formed neutron stars, but there is almost no evidence that says that this type of star turned into a black hole. So what do we think how black holes form in the universe? The most popular idea that's been around for many decades now is this idea that if you start with a massive star that eventually evolves into a red supergiant, as it approaches the end of its life, at some point the core becomes massive enough, it fuses into iron, so much so that in some cases, there is no successful supernova explosion. Instead, the core directly collapses into a black hole. The way that probably looks like is something like this, where you have a black hole that is formed from the implosion of the core as opposed to an explosion in the case of a supernova. And what you end up with is this rapidly accreting black hole in the center of a massive star that eventually gobbles up the rest of the star and leaves behind this black hole that we see in the black holes that we see in the universe. Now you can ask, what would this look like observationally? If you try to look for a star that turned into a black hole, what it would probably look like is that you have a star that was there in some archival image, and in a few years, you see it disappears. And this is actually the first reported discovery that I know of, which is where this is in the galaxy NGC 6946. It's only 7 megaparsecs away. What you see here is a red supergiant that was detected in HST data for many years before it abruptly disappeared over the course of a few years. This was discovered by the Ohio State group, which was using the LBT telescope to look for disappearing stars like this. They have a really nice light curve of this source where what you see here is the brightness of this red supergiant as a function of time. It's basically constant for many, many years until it undergoes this blip, small outburst, and then disappears. And it hasn't recovered yet. Star is gone. 20 solar masses of material, gas have disappeared into nothing. That's kind of the idea that you think of when you think of a black hole. All right. So let me tell you a bit about what we've been doing. So one of the cool things that you see in this discovery, is that these are multicolor light curves. This is optical, and you see there is this infrared light curve as well. This is from Spitzer in this case. What you see here is that even as the source disappears, there is this long-lived infrared afterglow that follows after the infrared brightening that happened around the time the star disappeared. And what we wanted to do is to use WISE to do this exact same thing, which is, can we look for infrared stars that are brightening in the infrared as a sort of a harbinger of a disappearance coming up? And that's what we've tried to do with WISE. So the idea is that we've been using WISE to discover massive stars in the nearby galaxies that have brightened in the infrared, and then follow them up from the ground, trying to look for whether there are stars that are disappearing. And I want to tell you the story of one of these stars. Here is, again, one of those WISE images. You see, this is an image from, I think, 2016. This is 2010. You subtract the two, you see there is a source that brightened, only one source in the middle. And I was like, okay, source brightened, let's go and try to take a spectrum of this. I was observing on the Keck telescope in Hawaii. And what my plan was that, okay, you see these three stars over here, these are the same three stars over here. The idea was that let's go and take a spectrum of this star, which presumably brightened. This is an image from 2010. I was like, it's going to be straightforward. I point Keck at it, put the slit on this thing and take a spectrum. And this is what it looked like in Keck. This third star, whatever that thing was, is gone. I stared at the screen for like an hour and I couldn't figure out what was going on because the star just disappeared. And if you can't see something with the world's largest telescope, it's really not there. So this was, honestly quite a frightening surprise to me at the time. But this really motivated a further investigation into what was going on. We pulled up all the archival HST images we could find of the field. This is the image, HST images in different filters. You see there is this booming bright source in HST images. In fact, in case you haven't followed, this source is actually in M31, Andromeda. This is the nearest galaxy to the Milky Way. A star disappeared in M31 and nobody noticed. That's where we are when it comes to disappearing stars, because it's a remarkably difficult exercise. There's this entire field of supernova enthusiasts looking for supernovae at gigaparsec distances, and a star died in our nearest Milky Way-like galaxy and it's gone, and nobody noticed. So we have a really beautiful data set that covers, because it's an M31, we have a beautiful infrared and optical data set. This is the WISE light curve, which is, you see there's this brightening and then it fades away. This brightening was what we got in the WISE data. And this is the optical light curve, which shows essentially it was there and then it plummeted and nothing after that. So we have HST images after. Just compare what you see before and after. Before, after, before, after. Source is gone. What we think this source was a 20 solar mass star. A 20 solar mass star disappeared into nothing in the nearest Milky Way galaxy. So, and this again gives you a sense of how difficult it is to find disappearing stars. Exploding stars are easy. You can, there'll be a supernova is brighter than its entire host galaxy, but a disappearing star, finding an individual star disappear at extragalactic distances, that's the real challenge. But infrared surveys, because of this infrared brightening signature, are a promising way to do that.
So in the optical domain,
yes,
you have this, which light curve is this one?
This is Gaia. This is roughly, this is B band, this is R band. And then this is ZTF data where, the source is.
Okay, so it's
yes.
upper limit only.
Yes, so it's an upper limit even in HST. Yes, so this source was 17th magnitude in HST. There is nothing there to 28th magnitude in HST today. Yes. So it's a fact 10 magnitude fading at least. And in fact, we have a JWST program that we're this hopefully going to get executed sometime next week to get a spectrum of this source. All right. So what can we tell from, what are we learning from this thing? So because we have this beautiful HST coverage from before the disappearance, we can get a very nice spectral energy distribution, SED of the source. This is what it looks like. Luminosity as a function of wavelength before the star disappeared. It's a very luminous star, about 10 to the 5 solar luminosities, exactly what you would expect for a supergiant star. And we think, depending on its properties, it probably started off as a 20 solar mass star. This is an animation of what that looks like. Towards the end of its life, there is a lot of evidence for intense mass loss, because we see a huge dust shell around it. This mid-infrared excess that you see over there comes from mass loss that's happening on the star. So the idea is that this star was undergoing intense mass loss just before it eventually decided to collapse. And the model that we have come up with is this idea that this is a yellow supergiant that has this depleted hydrogen envelope, which has lost a lot of its hydrogen envelope. And then somewhere around 2014 to 2016, which is roughly the time when it started to disappear, the core collapsed into a black hole, leading to essentially a disappearance of the star as this envelope was gobbled up by the black hole in the center of the star. We can verify that with actual models, and I encourage you to go read the paper. But the idea is that as this envelope gets accreted onto this newly formed black hole, the star eventually disappears from optical light. We can get a reasonably good estimate of the bolometric luminosity as a function of time, and we can show that you can explain the observations with a very weak shock that was injected into the stellar envelope just before it collapsed, and then that explains the formation of roughly what we think would be of the order of a 5 to 7 solar mass black hole that was produced from this. All right. So before I move on, any questions? See, everybody is just surprised.
Surprised.
31. Yes.
Guess what his name was?
Yeah, it
How
was.
come I know?
Yes.
Guess
Yes.
what his name was?
Yes. Right.
So yeah, I have a
Yes.
question.
Yes.
You
Yes.
showed many ticks, no random ticks, how the stars goes to a black hole.
Yes.
So you showed for some of the mass there will be black hole,
Yes.
other mass there will be neutron star. So
Yes.
that is theory or
That is theory.
theoretical?
Yes. Yes.
Okay.
So, and the problem is that the answer is different.
It is already given.
Sorry, what?
For neutron star or black
Yes.
hole, it's already given.
So,
Theoretically.
yes, but so that was, I think that's the traditional way of looking at it. There is no observational evidence for it, and I think more recent sophisticated models do not agree to that mass limit
Okay.
prescription
Do
at
you
all.
see a star with more than 25 solar mass to go through neutron star? Yeah.
I don't think there's any evidence for, well, there are these things called superluminous supernovae,
Yes.
which are,
But
which,
after the end product,
yes, so there are claims that the superluminous supernova light curves are powered by magnetars,
yes.
because only magnetars can explain the amount of energy that is being produced. So yes, there is indirect evidence, but
Yeah.
I don't think that's any direct evidence. But that's what I'm saying, like there is no evidence. I mean,
Yeah,
for
below 20, I
Yes.
would say,
Yes.
but more than 25 or 30,
Yes, yes.
I don't think there will be.
the strongest connection comes from galactic supernova remnants, actually. So we know of neutron stars inside the Crab Nebula. There is the Crab pulsar inside the Crab Nebula. So we know that some Skorkala supernovae produce neutron stars. But there is at least one claimed black hole inside a supernova remnant. So it's very, very gray at the moment, I'd say. There is very little evidence. So yeah, so I agree that the textbook picture is still there, but I don't think the textbook is that is really correct based on what we more modern simulations find.
So what is the, like, how long does this infrared brightening last?
Okay. So the WISE cadence is about 6 months, so it's not the best, but we think we can measure it to be the brightening takes place over the course of about 1,000 days. Yes. And then it disappears after that. Yes.
So did you check also within the 1 day light curve,
Okay, yes.
how much brightening was there during that time where it disappeared?
I haven't checked that because Unwise doesn't produce that. But
I mean, just to
Yes,
see
yes.
the light curve within
Yes.
the 1.2 days of.
That's a good suggestion.
Meaning.
I should check that. Yes, there'll be 12 visits inside
Yes,
each one day.
yes,
Yes.
90 minutes roughly.
Yes, yes. I haven't checked that, but I think we can pull it up. Yes.
Just few
Yes.
magnitudes maybe. Obviously,
Yes.
long term you will
Yes.
see larger
Yes,
variation.
yes. All right. So I'll move on. Let's see. So, okay. So I told you about how we think mass loss makes a huge difference to producing probably progenitors that turn into black holes. In this case, it was a yellow supergiant. It was not a red supergiant. Yellow means that it's lost some of its hydrogen envelope, so it appears hotter than a classical red supergiant. And what we are realizing as a community is that mass loss in massive stars is actually quite an important and a ubiquitous process. It happens to almost all massive stars. And essentially, this is the phase that comes over here, which is what happens in the very last stages of massive stars as they go from being red supergiants to stars that explode as supernovae. And traditionally, the way we infer the presence of mass loss is this idea of looking for supernovae that interact with their nearby circumstellar material. The idea is that if you have the same star, let's say a helium core with a hydrogen envelope, as this star explodes, if you have a dense CSM layer around it, what can happen is that this layer interacts with the pre-existing CSM and produces signatures that we can observe across the wavebands. This is a more sophisticated schematic of what that looks like. The idea is that you have this supernova shock that's crashing into the nearby circumstellar material and producing spectroscopic lines. These are the so-called type 2N supernovae, which have these narrow lines in their spectra. We infer the presence of this interaction based on those lines. And this is, based on these measurements, we can tell that pre-supernova mass loss is actually quite common in massive stars. And that's something that's become of a cottage industry these days. But what I want to convince you is that infrared surveys again are telling us about new regimes in circumstellar material that have been previously overlooked in optical searches. And the way to convince that is that, I showed you this simple picture. Yes, supernova interacting with CSM, but keep in mind that you would only see the interaction if the ejecta are far out enough that it's already crashing into the nearby circumstellar material. And the reason why that's non-trivial is that imagine if you had a supernova that looked like this, where the CSM shell was much, much further out. So instead of the supernova immediately crashing into the nearby circumstellar material, producing these exotic lines that we can see, if you had a shell that was very far away, you would actually, even if the shell is there, it would be very difficult for us to conclude that there is this shell around there, simply because the supernova still hasn't reached it yet. It would take probably a decade to reach this shell. But yes.
Like in this case,
Yes.
wouldn't the supernova explosion photoionize the shell and we can still see nether lines?
Photoionized.
Like the light from UV light. Or,
Yes. So that I think this still depends on the amount of radiation the shell is receiving. So if it's very far away, the ionization flux will not be high enough to produce enough lines. So you're right. So I think we're here. I think I'm thinking of shells that are of the order of a parsec away, which is like factor of 100 typically larger than what we infer from the type 2N supernovae. So right. So in this case, what we see is that even though we wouldn't see the direct effects of this interaction, what can happen is that because gas in the universe is very commonly associated with dust, what you would expect is that even if the supernova is not interacting with the CSM immediately, and we usually do not follow up supernovae out to decades after explosion to really infer the presence of these lines, what we've been trying to do is to use infrared emission, because we think that most of these gas shells are also accumulated with dust, which is that whenever you have cool gas in the universe, it comes with dust. And the idea is that even if there is no immediate interaction between the supernova and the dense circumstellar material, years after the supernova actually occurs, you can use infrared surveys to start seeing the dust emission light up as the supernova starts interacting years after the explosion, when typically you would not follow it up with spectroscopy. And the way we've been pioneering this is, again, looking for transients in WISE data that are occurring coincident with nearby galaxies. So here is another example. You'll see many of these today. This work was done by Charlotte Myers, who's an undergrad at MIT. We've been looking for these transients happening on the top of galaxies in WISE data. You see there is this supernova that appeared in WISE. It was not known in any other survey, so it was a bit peculiar because this is clearly an infrared discovered event. And what we can show is that if you plot this object, the light curve of this object compared to all other known supernovae in the infrared. So this is absolute magnitude, essentially luminosity as a function of time from discovery. Most supernovae tend to be very faint in the infrared at late times, except the ones that show interaction with circumstellar material. And this object, just based on how bright it was and how long-lived it was, we can show that the only way to explain why it has such luminous infrared emission at late times is that there is this dense CSM shell that was very far out, probably about a fraction of a parsec away from the star. So you would not see the effects of the interaction immediately between the supernova and the material because it's so far away. But because NEOWISE essentially keeps surveying the sky again and again, essentially keeps doing it all the time, you essentially, for free, you can identify these things because infrared photometry turns out to be a very effective way of detecting dust being lighted up by the interaction between the ejecta and the CSM. So obviously, when you find something like this, our first program is to do spectroscopy. And in this case, again, we went back to Keck, got a spectrum of this source, and lo and behold, classic type 2N supernova. So what you're seeing here is in black is a spectrum of this object that was identified from the mid-infrared. There's no optical signature of it. But what you see when you take an optical spectrum is that it is booming H alpha line, which tells us that there is ongoing interaction that is photoionizing the hydrogen in the shell and producing this broad hydrogen line that we can see in the spectra. And it looks essentially identical to other interacting supernovae we followed up to late phases, except in this case, this was really followed up only because it brightened in the infrared. Nobody else was really looking at this object because the shell was so far away.
So like, could you
Yes.
see this source in the optical images as well?
It's very faint. It's like it's a 23rd magnitude optical source, but it's a 17th magnitude infrared
Okay, so
source.
that's why it's probably was not discovered.
Yes, right. Well, so no, so it was detected in ZTF at peak at around 20th magnitude, but nobody really got a spectrum of it because there are too many 20th magnitude transients in this. But we know this is interacting because there are not many things that are minus 22 in absolute magnitude in the infrared. So that makes it a really powerful way of looking for these things. So so again, the entire point of WISE is that it's all sky, it's very systematic. So we can actually start quantifying things like how common are these things. And that's again something that we did in this paper, where we showed is that there is this kind of overlooked population of events that actually show these remarkable late time mid-infrared brightenings that we do not otherwise spot in optical surveys. So here are a bunch of optical light curves of supernovae in blue. The red are the infrared light curves. In WISE, we can see this population of events that show late time interaction. And we can quantify that about a few percent, I think probably of the order of 3 to 5% of all core collapse supernovae undergo this type of late time interaction that are not detected in optical surveys. And that's big because that basically means that the number of interacting supernovae out there in the universe is probably double of what we actually infer from optical surveys, because the shells are so far away, you don't actually detect their presence until very late times. All right. Before I move on, any questions? Yes.
You acquired the spectrum for
Yes.
that very faint.
Yes. Yeah.
Can you acquire a spectrum for that faint at that faint?
So so the 22nd magnitude is correct, but most of the flux is in one emission line, H alpha. So the effective flux in that H alpha line is actually quite bright. But when I say 22nd magnitude, it's R band 22nd magnitude. So
Infrared bright. Infrared bright also, right?
yes. So
And also cake. You are using cake.
yeah, this is cake. Yes. That was a 1 hour spectrum with cake, so it is a very long exposure. Yes. So no, what helps us is that that R band of 22nd magnitude is all of the flux is in just one wavelength, which is H alpha. So that helps in the detection. Okay, so let's go to a bit lower mass stars. So you might be thinking, okay, so sure, massive stars are violent, they do all kinds of weird things, they explode, they erupt and all that. But what I'm going to try to convince you is that even low mass stars are not any less interesting when it comes to infrared transients. And I think low mass stars are probably even more interesting when it comes to infrared transients. So let's move to this part of the diagram, which is, again, let's think of what happens to the sun at the end of its life. So sun turns into a red giant, eventually turns into an AGB star. And what we think happens is that these AGB stars sort of expel out their outer envelopes and produce things that we call planetary nebulae. And inside that planetary nebula, you have a hot white dwarf that's formed, and that eventually leads to the death of the star. So, in a classical scenario, sure, there is a star sort of expands into an AGB star, it would produce a spherical shell around it and lose most of its mass. But it turns out that if you actually look at real observations, this is far from the reality. If you look at what a planetary nebula actually looks like with HST or JWST data, this is what the structures look like. So you can ask, okay, so I have a single AGB star. It's just sort of losing mass. There's not supposed to be any directional preference for anything. Why does every planetary nebula look like this? These are very strange shapes. Look at these, it looks like bipolar. This is called the cat's eye nebula for whatever reason. And you see there is a very exotic shape. So why is that? And it turns out that the most promising way, the way I look at it, to explain why low mass stars, sort of the most common stars in the universe, end up as these exotic looking end products, is that most stars, I think, even for sun-like stars, are actually born as part of binaries. And you can ask, why does this matter in the case of the stellar evolution aspect, which is that if you had a sun-like star that is expanding, trying to become an AGB star, and suddenly it encounters a companion next to it, what happens? The companion has to do something with, because the mass is just being dumped with mass. And what we think happens in most of these cases is what is called a common envelope phase. So what I'm talking about is something that looks like this. This is a simulation. This is not real data of a star that is expanding and eventually engulfs its companion into its own envelope. what it also does as part of that, you see it's producing these outflows that are not spherical at all. So, in fact, this is, it could be a star, it could be a planet, it could be a comet, for what, it doesn't matter. But the point is that whenever you have a binary companion, it completely changes the geometry of the outflow. And that probably affects why stars look the way they look at the end of their lives. And fortunately, this process itself is actually quite remarkable when you look at it in terms of transient studies as well. These are called stellar mergers, the so-called luminous red novae, that if you've heard of that term. And what these look like in actual observations is something like this. This is not a simulation. This is a real Hubble Space Telescope time lapse of a stellar merger that happened in our own Milky Way. This is the star V838 Mon, which erupted in about 20 years ago in 2002. What you see here is Hubble Space Telescope images taken over the course of a decade. What you see is in the center is the remnant of the merger that happened between the stars, very much what you're seeing in the simulation. And this expanding shell is essentially an echo of the dust cloud that was next to it. The point being that these are called luminous red novae because they kind of look like novae in that they brighten all of a sudden. But as you can see almost visually, this is a very red source. Novae are not red sources. Novae, the classical novae are very blue, whereas these guys tend to be very red because they form a lot of dust in their outflow. We can almost see it here. There's a lot of cool gas that's being ejected and it forms dust as this merger proceeds. So we can now actually routinely identify these luminous red novae in optical surveys like CTF or all of these all-sky surveys that are happening today.
No, but here,
Yep.
if you go back to
Yes.
so here it starts with almost this spherically symmetric shell, and then it becomes symmetric later on.
Yes, that's right.
But not initially. So
Yes.
could that be also because of the environment in which it is expanding and the ram pressure of the outside surrounding, and that could affect the shape, or is it only because of the
Sure. Yes.
the explanation that you gave only because of the binary?
So I think the way I'm thinking of it is that it appears that in most of these cases, you see how the geometry is essentially symmetric around the central source. Like if it was something that was mediated primarily by the ISM conditions, there is no reason why should be any symmetry about the central source. Like you see, there's a symmetry.
Yeah, this
axis
one is
here.
very
Yes, or
different, yeah.
even there's a symmetry axis that is centered on the central source, which makes us think that it is a process that has to do with the star rather than the surroundings.
Okay, so then you mean
Yes.
to say the sun will also end up in making nebulas like this?
Well, the sun doesn't have a
Yeah.
companion, not that we know of. But actually,
So what if there is a Jupiter and then sun?
yes. So I think that's probably yes. That is true. Well, our Jupiter, I don't think is close enough that it would interact with the sun in the AGB phase. But if the Jupiter was, Earth mass planets are insignificant. For
Yeah,
something
yeah,
like
yeah.
this,
That's
but,
why I said it.
and I'll come back to Jupiter stuff in a bit. But yes, but you're right. Like if there was a Jupiter nearby, it would produce a very similar effect.
Right.
All right. So what was I going to do? Yes. So yes. So can we? So the idea is that can we link up these observations of luminous red novae that we find in optical surveys to these fates that we're seeing? These clearly all kinds of low mass stars undergo this common envelope, this stellar merger phase at some point at the end of their lives. And the way we can ask that is this paper that I did with my colleague Morgan at Harvard. What we were trying to understand is if you take these population of luminous red novae that are discovered in optical surveys like ZTF, do we see evidence for these stars that eventually would produce these planetary nebulae from low mass stars? So just to show what that looks like, here is a HR diagram. It's a color magnitude diagram, which many of you would have seen. What you can do is that you can plot stellar tracks on top of this. So this is a 16 solar mass star, 4 solar mass star, 1 solar mass star. So 1 solar mass star, like the sun, follows this trajectory in this plot. And if you look at the population of these stellar mergers that we find in optical surveys, are any of those consistent with these low mass AGB stars that are engulfing their companions? And it turns out that all of these diamonds that you see, these are progenitors of stellar mergers we've seen in optical surveys. The point being that basically none of them are actually AGB stars at all. They all tend to be these stars that are closer to the main sequence, these what you would call subgiant or Hertzsprung gap stars. So these are in no way stars that would produce the kinds of planetary nebulae we would eventually expect sun-like stars to undergo, because those stars they all live over here. Like the common envelope is occurring at the very end stages of their lives, but we clearly don't see that in optical searches at all. They all tend to be more compact, hotter stars than what we would expect. And what Morgan, my colleague, who's an amazing theorist, what he came up was this idea that, where can we find these stellar mergers, the red novae, from these evolved AGB stars that we supposedly are the progenitors of these planetary nebulae that we see. And the idea that we came up with is that because these two stars, just when they're undergoing this common envelope, you can see this is a simulation. What you see is that as these stars actually dance around in their very final phases, what you get is that they expel lots of cool gas and dust that essentially, and that cool gas and dust can obscure the star in the optical bands. So much so that by the time that the common envelope episode actually happens, the star is entirely obscured. And this is what is shown in this right plot over here. All plotted on this stellar track, this color actually shows you the amount of dust obscuration we expect as the stars become bigger and bigger. In terms of the visual magnitude of extinction, essentially showing that for sun-like stars at the end of their lives, we expect them to be obscured by several tens of magnitudes of optical extinction. So much so that even if the stellar merger did occur in the very final stages, we wouldn't actually ever see that because it's just obscured by dust. So that essentially motivates us to look for these stellar mergers in the infrared bands directly, because the infrared light is still emerging from these sources, as opposed to the optical bands, which are completely obscured. So we've been searching for these luminous infrared outbursts in the galaxy and in nearby galaxies. I won't go into the details, but what I'll summarize is that yes, we've now identified a population of these red nova-like events in very nearby environments. This is one that is in our galaxy. It's only 2 kiloparsecs away, just to give you a sense. A stellar merger in our galaxy, 2 kiloparsecs away, went off in 2016. Nobody noticed because it was very obscured and just there in the infrared bands. This is the same type of object in M31, again, our friendly neighborhood galaxy. And this is a similar object we think in a galaxy that's about 3 megaparsecs away. These are quite remarkable infrared transients. You see the galactic object, which is on the left over here. It's a booming bright, it's saturated in WISE. That's how bright it is. But essentially, because it's just there in the infrared, these things go unnoticed in optical searches. And things like this, this is again the same object in the infrared, where you see it's a very bright infrared transient, like 15th magnitude in the infrared, but very difficult to spot in the optical bands. So, in a nutshell, why we think these are stellar mergers is that, when we do optical and spectroscopic follow-up of these sources, they look exactly what we see in other stellar mergers. Namely that as this is an infrared light curve of one of the sources, it starts off in the mid-infrared, has this huge 5 magnitude infrared outburst that makes it one of the brightest infrared sources in the sky for some time. And if we dig up old archival data from the optical bands, you again see it has a very small optical outburst, but it very quickly disappears in optical light because it forms dust so quickly.
So their rate is also consistent with the merger, or?
I don't think anybody knows the merger rate, but okay. I think the merger rate is probably once every few years in the Milky Way.
Yes.
That's a very interesting. One of the reasons why I got interested in this was because if you look at papers, they say the merger rate in the Milky Way is once every few years.
Yes.
The last known galactic stellar merger before these guys was in 2007. We are 15 years overdue for a merger.
Another merger.
Yes. So, and I think we've identified a few more of these now, which are just there in the infrared. So it's not surprising in that sense.
And if you go from our galaxy to another galaxy, it is similar, or?
So I think so the mergers like to happen in galaxies that are more star forming.
Yes.
There is a preference for that. So more star forming galaxies appear to host more of these merger type events.
Mm-hmm.
Right. Anyway, so long story short, we've gotten spectroscopic follow-up. These are the spectra of these things. They, without going to the details, they look like M stars at the very end during the outburst because they produce a lot of cool gas and dust. And the final the nail in the coffin really for all of this is that this is that same diagram that I was showing, HR diagram, luminosity, temperature. All the optically discovered red novae lie over here, the more hotter compact stars. And our events that we're finding in the infrared, they all consistently lie on these AGB red giant AGB star region of the of the HR diagram where we don't see any optical mergers at all. Really confirming that, yes, these mergers do happen in this phase. It's not surprising because we see planetary nebulae in these weird shapes. So, but we can finally making the connections between stellar populations and the planetary nebulae with observations of these transients directly. All right. So, okay, so let me see. I'll just cover one more thing and then I will call it. But okay. So one of the other things, and I think, okay, so there was this question came up about Jupiter, which is can the presence of a Jupiter-like planet affect the evolution of a star? And this is actually not, this is a question that's been around for many, many years. And that's because we know that there are planetary architectures that look like this. For any of you who are interested in exoplanets, maybe you know this. This is TRAPPIST-1, very famous system, one of the first systems harboring multiple terrestrial worlds. So, because of all these exoplanet survey missions, we know that close planets around stars are very, very common. There are these population, if you look at Earth-like planets, they're probably, at sub-Earth distances, there are probably every star has one of those things. The ones that are even closer in, these things called hot Jupiters, which orbit very close to their stars. They're, remarkably well. They're easier to find in transit surveys because they're big. But generally, the idea is that almost, it's probably not incorrect to say that almost every star has a planet around it. I don't think that would be incorrect to say, given the number of planets that we find in these surveys. Now, a fundamental prediction, of course, then of what happens to these planets at the end of the star's life and what will also happen to the solar system planets is this idea that as the star evolves off the main sequence, it becomes a giant and engulfs its planet as part of that process. And this could produce some kind of an optical transient that we can discover in surveys. So, and if you think of the process itself, what I described to you just now, the stellar merger process, you have a star that's entering the envelope of another star. The process in the case of a planet engulfment is kind of exactly similar, which is you have a planet entering the envelope of another star. The only difference being that a planet is about 1,000 times less massive than a star, and sort of the long-standing predictions have been that these would essentially look like stellar mergers, but just on an energy scale that is 1,000 times smaller, because the planet, Jupiter, is about 1,000th of the mass of the sun. So as part of this effort to look for these infrared transients that could be associated with stellar mergers, here is a story of remarkable galactic transient. So here's a star that is no reason to really be interested in this. It's just there in the one of the Euclid archival images. And somewhere around 2020, it underwent this remarkable outburst that was, well, I first identified it in ZTF data. You see there is nothing, no detection. And suddenly in 2020, it undergoes this outburst and slowly fades away. Now, by itself, it's not particularly interesting. Okay, it's an optical outburst. It looks somewhat red. You see it's brighter in the infrared, near infrared bands compared to the optical. But what really ticked us off was this thing that it has this very luminous and long-lived infrared source that follows it. You have an optical outburst that happens and then disappears. The infrared counterpart, on the other hand, stays on and stays on for years after the actual event. It almost smells like one of these stellar mergers because that's exactly what they do, which is they go into outburst, they form dust, and they stay very long-lived in the infrared, whereas the optical counterpart disappears. The only catch is that this is a star in the galaxy, and it barely got to 17th magnitude. It's a remarkably low luminosity event. So even so much so that, regardless of what distance you put at it in the galaxy, it's like 1,000 times fainter than what you would expect from a stellar merger. And this is exactly what we believe to be the case, which is that it's a stellar merger, except it's a factor of 1,000 fainter than what we expect to see in stellar mergers. And the picture is that this is a nice animation we made for the paper that came out. We know of these planets that are called hot Jupiters. They are bound to eventually crash into their host stars because of stellar evolution. And as these stars evolve off the main sequence, we expect that in the very final stages, the planet essentially grazes the surface of the star for a few orbits, and eventually it gets engulfed into the star itself, producing this luminous optical brightening that we can find in surveys. And all of the data that we collected was consistent with this picture that you had essentially a merger of two objects, except it was the thing being engulfed was a factor of 1,000 fainter than what you would expect for a stellar merger. Now, of course, this is kind of prophetic in that, this is the long-standing prediction for what happens to the inner solar system planets, because, the Earth is at a distance where the sun would, if the Earth stays where it is, then the sun would engulf the Earth in 5 billion years from now. So obviously it got a lot of press attention, and we were lucky in that Nature was kind enough to put us on the cover of Nature. And there was a lot of interesting press attention, which I think was, was fascinating to deal with, because there's a number of news articles that covered it. And honestly, I mean, I don't mind all of this. I think the thing that I was struggling to convince journalists about is that this is not something we have to worry about right now. This is happening in 5 billion years. And I had to convince them that the sun's expansion is not what is causing global warming. So those are two completely unrelated effects. Anyway, this was a fascinating result that I think got a lot of public attention. All right, I think I have some other stuff, but I think I'm going to let it go. I think we have maybe, yes.
Go ahead for a few more minutes. Maybe.
Okay, let me tell you a bit about future instead of this stuff. Oops, yes. So anyway, I didn't get to talk about a lot of the other results that keep us busy. We have, in case you're interested in supermassive black holes, we have a huge industry of tidal disruption events that we're identifying in the infrared bands. If you're interested in type 1a supernovae, not the massive stars, we've used infrared surveys to look for CSM interaction in type 1a supernovae that have been overlooked. I have this long-standing interest in galactic X-ray sources, looking for X-ray binaries, and again, infrared surveys have been quite powerful to do that. Again, because infrared lets you penetrate through the dust in the Milky Way. So, but what I really want to end is really looking forward, which is that infrared has just started. I think we're just scratching the surface of what we can do in the infrared science, and there's a lot of coming facilities that will really push this field even further ahead. In about 3 years from now, we will see the launch of the Roman Space Telescope, which will have the largest infrared camera ever built for astronomical surveys. It has essentially, this is what a simulated Roman event would look like. This is the field of view of Hubble, essentially 100 times the field of view of Hubble, which is tailor-made for doing infrared surveys. So in case you're not familiar, this is essentially the same aperture as Hubble, the same mirror size, but with a field of view that's about 100 times bigger, and is optimized for infrared surveys, because that's where many of the new discoveries lie in the next decade. So I like to think of sort of how quickly this field is growing in terms of the size of the infrared cameras that have been created over the last few years. If you plot the number of pixels of the camera as a function of its field of view, traditionally, if you look at, let's say, typical 2 to 4 meter class telescopes, this is what the traditional practice in infrared science has looked like, which is you have these very small field of view, large number of pixels cameras. But there have been few attempts at doing these larger cameras, which are these larger field of view, larger number of pixels. This camera has unfortunately been decommissioned permanently for another instrument, so that's sad. But what I did during my PhD thesis, which I did not talk about at all, is this sort of pushing this into a new regime, which is going into very large field of view, but very small number of pixels. It's called Gettini-IR. It's a robotic infrared survey that's still running. And you can ask me about it if you're interested in like shallow infrared light curves of things. I'm particularly oops. This is where Roman is, just to give you a sense of scale, which is, it's about a factor of, oops, that's what it's saying. There you go. Yes, so Roman will be exponentially bigger when it comes to infrared cameras than anything that has existed in the past. But it is, Roman, even though it is big, it's still much smaller than what the state of the art in the optical is. ZTF is somewhere over here, like something that exists today. And LSST is again way outside, somewhere on the roof. That's how big the camera is. So, infrared is coming. It's still not big as optical, but I'm hopeful that it's the future is bright. So these are two ground-based infrared surveys that I'm really excited about. We're actively working on making the pipelines for these, doing image subtraction, trying to look for transients. The key thing about these things is that they're using small telescopes with big detector formats to cover as much of the sky as possible. This one actually is using a detector that's never been used for large surveys before, so that's traditional infrared detectors, which tend to be expensive. And we have now have these real time. So a lot of the WISE discoveries came from these archival searches where we find things years after the event just because the cadence is so slow. But my hope is that going into the next few years, we are running these pipelines where we can find transients in real time. Here is an example from one of these prime transients. We see again, same science, reference, difference, source, nothing, boom, goes into outbursts. But this is on the time scale of weeks as opposed to years that we've been doing in the past. And we can follow them up with spectroscopy. This is a Magellan spectrum of what was confirmed to be a galactic nova discovered in infrared data. So anyway, I will leave it there and take any questions. These are nice animations of some of these stars that have brightened in WISE. These are actual WISE images to give you a sense of how bright some of these sources are, but still unexplored. Thank you.
So thanks. Now, questions.
Your science and reference images are not same exposure.
The reference images are typically much deeper, just to get better quality. In image subtraction, it usually helps to have a better quality reference image to reduce the number of artifacts.
More questions? Yes.
You said the mass of that disappearing star was about 20 solar mass. How did you estimate it?
Let me explain that a bit more. So we can compute the current, we can estimate the current luminosity and temperature of the star. And based on that, we can compare it against stellar models for the end stage of what type of star would end up with a luminosity and temperature of at the value that we observe. So based on that, what we can tell is that it's a star that was initially formed with a mass of 20 solar masses. It eventually lost some mass over the course of its life because it's undergoing mass loss. But at the time of disappearance, we think the star was closer to 6 to 7 solar masses because it's lost more than half of its mass due to winds over the course of its life. So yes, it's based on the luminosity and temperature. Those are the main observables we get from the data.
Any more questions?
So you said like the getting surveys in there. Like,
Yes.
Are there any other like IR surveys which are running currently or in real time?
So Gatini-IR is still running, except the transient discovery part, we are manpower limited at the moment. And so because I finished my PhD, I don't have time to look at it right now. But yes, so the two surveys that I mentioned, the ground-based, these two surveys I think are the ones that are actively being monitored and running.
So
yes.
I thought you said they were like upcoming, right?
No, these are running. No, sorry. So sorry. Yes, so these are very new in that they've only started in the last year or so. So the pipelines are still being brushed out a bit. So I wouldn't say they're like running, but they are producing things. Yes.
So
Yes.
you mentioned about you just touched upon studying infrared signatures in like black hole binaries. So
Yeah.
so
Yes.
what do you infer? Do you infer the brightening of the accretion disk structure or not?
Okay. So in the WISE bands, which is 3.6 and 4.5 microns, what we've done is we usually see the jet evolution. So in the mid-infrared, the emission tends to be, it depends a bit on black hole binaries have these weird states and soft and hard and whatever. But for the most part, it's emission from the jet. So we've essentially used the WISE light curves to understand how particle acceleration works in jets, because that essentially is that constrains the peak of the synchrotron spectrum in the jet, and that lies somewhere in the WISE bands. So that's very interesting regime to observe in. But that's nice. But what I'm really interested in is looking for new black hole X-ray binaries undergoing outbursts in infrared data without X-ray observations at all, because I think there is a lurking population of these faint X-ray binaries that we don't see in X-ray surveys, where infrared surveys may be more interesting to look at.
Like this binary you told about. No?
Yes.
So you can have neutron star and then its jet is active for longer duration. But when it's called about the black hole binary, how long the jet stays active, like the duration? Because the matter, how much it can
Right, we haven't looked at the neutron star binaries because those are too many, and I think there's quite a lot of diversity. The one paper that we did was on the roughly, I think 20, not 20, I think there were about 30 known black hole X-ray binaries with optical infrared counterparts.
Okay.
And there, so yeah, the main thing we found in that is that whenever the source is what is called a hard state in the X-rays, the infrared emission is completely dominated by the jet, and we can say that because the WISE gives us two colors, right? So we can compute a spectral index for the emission, and we can see these dances in spectral index when the source switches between.
So it's a
soft and hard
non-thermal
state.
or?
It's non-thermal, yes,
Fully
yes.
non-thermal.
Yeah, yes. So in the mid-infrared, yeah, it's all non-thermal. Yes.
Any further questions?
Also, I'm around here tomorrow. If you have a science idea, you could use infrared data. Please come talk to me.
So, yes, so he's here, he's sitting in the visitor room in the new old building. I dropped him an email. I think the visitors copied it. He's copying the email, right?
Yeah.
So if you want to discuss more, then contact him directly. So I'm just wondering if you have any IFU observations on the nebular part, any of these sources, going by bright sources, or anything else planned to do anything?
I would like to do it. I haven't done it yet. Yes, so I think some of these galactic transients, especially the stellar mergers, they have extended sources around them, which I think has to do with the pre-merger mass loss around the stars. We can barely see it in ground-based seeing data. You can see some structures, but I think
JWST.
Yes. So JWST time is that lottery these days. It's like, yes. So it doesn't matter how good your proposal is. Like, so it depends on the mood of the reviewer. Yes. So yeah, we're hopeful. We'll see.
Okay, so if there are no further questions, let's thank the speaker again. Okay, so that. Thank you.
Wow.
Yes.
All done.